for coming. So indeed, this will be a bit more on the theory side. So let's start about, this feels like dinosaurs of neural networks today when we talk about foundation models, but still, okay. I just want to remind you that you know these pictures, and that's a neural network. It means that it represents a function that is written here, and the way we train this neural network is that we minimize over all the parameters, all the weights, some kind of a loss function that compares the output of this function to the desired output, the labels. And then what these two first points are telling is that also something as simple as linear regression, so just fitting points with a line, and I will be coming back to it, is a special simple case of a neural network where the function is just simple as that. Or generalized linear regression if, for instance, we want the network to output labels that are plus minus 1, we may need to add here a function here. So it's not quite linear regression, but generalized linear regression. So this is the kind of settings that I will be thinking about, right? And you have heard many talks about them. And maybe in a bunch of those talks, you heard about these adversarial examples. So this talk is not about adversarial examples, but it illustrates nicely my point, right? So you have seen pictures like that where you train a neural network to classify images, and then this classifies this picture correctly as a panda. And then you pick a particular instance of a noise that is very, very small. You add it to the panda, it still looks like a panda. But now the neural network outputs, it's a gibbon, with some confidence, 99.3%. So this is just a picture, kind of a screenshot from Google. But my question here is, what does this actually mean? Where does these percentages come from, right? This looks like some measure of confidence. But okay, those of you who train neural networks every day know, but if you don't, then maybe it's not immediately clear to you. So what does this mean? So what we always do when we train neural networks, as I said, we minimize these empirical risks. So this FW that can represent as complicated neural network as you want, it's just parameterized with W's and it takes the inputs X. And then we minimize the loss, perhaps with some regularizations and the losses that we kind of all love. When it is regression, usually we use square loss, and when it is classification, usually logistic loss or cross entropy. And then these percentages, 99% gibbon, come from the fact that the cross entropy loss is written in a form where certain parameters in the logarithm, called the cross entropy scores, usually, that are written like this, they are actually numbers that are positive because it's an exponential of something and normalized, so they sum to 1. So if you wanted, you could interpret them as probabilities, right? And that's the probabilities, this 99%, that's the probabilities that people report when they say the neural network thinks this is a gibbon 99%. Right? But now the question is, is this a probability of something in some fundamental sense? Does this actually mean something? Or is it simply a positive number that is normalized, that is not enough to mean something? And then, in this slide, I explained to you that very generically, this is actually completely nonsensical number. So especially in the context of overparameterized neural networks, which are all the state-of-the-art architectures that we are using today, meaning that they have so many parameters that even if the labels were completely random, we would still be able to train them to 0 error. Okay, so there are so many parameters, so this kind of does not really correspond to some Occam's razor minimal number of parameters. So this is something that we know. It must be somehow helping the gradient descent, and I could have given a different talk about what we actually know about that. But they are overparameterized, that's a fact. So overparameterization means that you can go to 0 training error even for completely random labels. So you go to 0 training error. Now, if you actually have an intuition about the mathematical form of this cross-entropy loss, you will immediately see that the only way this function can go to 0 is actually if these logistic scores go to 0, 1, 0, 0, 0. So that's the only way this logistic loss can go to 0. So if we train till convergence, by definition, the neural network is absolutely confident about its output, even though the test error may not be at all yet close to zero. Okay? So something like stopping early or regularizing properly mitigates this a little bit, but not quite enough. So quite generically, if you train an over-parameterized neural network, these scores will be overconfident. So you cannot actually reasonably think these are good measures of uncertainty. So this 99.3% just means nothing. Okay. So we need to do something about it. So deep networks need to be calibrated. We need to get some uncertainty measure that actually means something. So what does calibration mean? So Saturday I was going to ski and it was not so clear what the weather will be. And so I was checking the weather, right? And what these error bars here mean, these bars, blue bars, when they say it will rain 25%, well, the Meteo Swiss, they better do, or Google in this case, they better do it in such a way that on 25% of the slots where they say it will rain 25%, it rains. Right? If it rains on average more often or less often, then people will not be happy if somebody kind of does the statistics. So I was lucky, it was actually not raining, it was a pretty good cool day for skiing in the afternoon, despite the prediction that was so-so. So that's what calibration means. Now, in the context of neural networks, now one slide about the current thing. So from the GPT-4 technical report, people actually do care a lot about calibration of the foundation models today. So this is just what is said in the abstract of what GPT-4 actually is, right? It's a transformer that is pre-trained to predict the next token in a document, that's all. So that's the pre-training. And then in the post-training alignment process, it is designed to improve performance on measures of factuality and adherence to desired behavior. That's what their abstract says, right? And then somewhere in the middle of the report, they have this interesting picture. That's the way in statistics we usually plot whether things are calibrated or not. So if it is a line, it means that it's well calibrated. If it is not a line, like here, it means that it's not well calibrated. And the left-hand side here is for the pre-trained model. So here we see that the pre-trained model is pretty well calibrated. But for the post-trained model, for the fine-tuned one, that is designed to improve the performance, the calibration goes away. Okay? This is not a line anymore. This has the shape, again, it's overconfident. And indeed, you know that, discussing with ChatGPT that it's not aware of its uncertainty, absolutely not. So this is, of course, a big topic in machine learning, and there are many papers, and here I just really picked really few of them, those that are very influential by judging by thousands of citations and users that they acquired. So you can think, oh, we should maybe not minimize losses, but rather sample over some probability distributions like we do in Bayesian inference. Or we should kind of bring in some uncertainty that comes from the fact that if we initialize the training process differently, then we get a different output. So that's what this idea of deep ensembles is based on. Or we should do some temperature scaling. That's one that I will actually get to in a bit more detail. And there are many, 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 many more I could have cited. But the bottom line is yet ChatGPT still hallucinates, so that means we just did not figure it out, right? So there are ideas, but none of them actually works. Because if it worked, then we would have a foundation model that actually does not hallucinate, and that's not the case today. So this is complicated. Many people thought about it, so now I kind of go back to my theoretician mind, and I use here an event from last week. Those of you who follow mathematics follow that there was the Abel Prize awarded last week to Michel Talagrand, who also happens to be actually one of the persons who proved a lot of the things from the field of statistical physics, where statistical physics predicted it, so we were kind of all happy. And I loved in one of the interviews, he said that the way he worked was trying to understand really well the simple things. And for me, that kind of is the essence of science. Unless we understand really well the simple things, how can we hope to understand decomplicated things. And so I bring you back to the linear regression. And this slide, that's a slide from my colleague Iva Tkalček, who teaches the physics experiments in our second year physics bachelors. Okay, so if we have in the room, probably we have people that went through the physics bachelor in EPFL, you have seen that slide or some equivalent of it. Right, so we teach our students before they do any like basic physics experiment that if you have data that look like that and we need to fit a line, then the coefficients A and B of the line, in order to get them, you need to minimize the least squares, right? That's just minimizing this least square loss. And then you get the prediction A and B. In this case, you can write it explicitly. And then in yellow, they give you this way how you should actually estimate the variance. And then, right, physics students go, just compute this thing, plot the error bars. And here we are in a session on scientific machine learning. So in science, the error bars is very important. So you would think that's one of the simplest things. There's the second year physics bachelor. So, okay, so let me ask you a question about that. So once again, this is a formula that I think all the physics students used. So if you have physics background, you have used it. So which variance is that actually? So we have some data here, so that would be the inputs and the labels, and then there are coefficients. Let's assume that the data actually, so there is some ground truth coefficients that describe the true physics. They may not, the true physics may not even be a line, but okay, there are some ground truth coefficients, let's assume. And then there are the ones that we estimate. In statistics, we write this with the hats. And then I have three cases here. Okay, it's kind of a formula, but let me explain the essence of these three cases. Okay, so variance over what? So in statistics, what we would often want to have, say that we run some medical trial, and we would want to have the information about if we redid everything from scratch, chose completely different people for the trial, if we just redid everything once again, what would be the difference in the result? What would be the variance? So redoing everything again means that we are really redrawing our inputs X and redrawing our labels Y from scratch. And then we are interested how that influences and changes the result. Okay, so that would be the notion A. That's kind of the most commonly taught in statistics, in the math department. Notion B would be when the inputs X are given, but the labels are redrawn. So we assume that the inputs are there, they don't ever change, but there is some underlying process, random process that actually gave us the labels. And now we assume that the noise on that was redrawn and the labels were redrawn. So that will be our notion of variance. And then the third one is when actually the data is given once forever, right? So the MNIST is there. All of you probably worked with MNIST. You have not been redrawing the MNIST and asking people to redraw the digits, etc. It is there, both the inputs and the labels, and yet there is still an uncertainty about what the prediction is that comes from the fact that while you have 1,000 or 700 dimensional MNIST images, you only have about 50,000 of them. So the number of images is not that much bigger than their dimension, in which case you cannot get exactly zero test error. You don't, right? Even the best systems still get like 1% or so. And so there is intrinsic uncertainty even for the given data set from the fact that you are not able to estimate perfectly the ground truth. So now, which of the three is actually the physics formula? So who votes for A? No one, maybe, okay. Who? Yeah, some vote for A, some, okay. Who votes for B? More, okay, good. And who votes for C? No one. Okay, so you're right. Those who are awake are actually right, it's B. So the way we derive this formula, and I think I have it on the next slide, I actually teach it also to the second years in kind of the theory part of the data analysis class. Yes, to derive this formula, you indeed assume that the x's are fixed, the inputs, and that you redraw the noise, and that there is some ground truth W star that indeed produced your labels, right? You do all those assumptions, this may not be true, but under those assumptions, computing this variance actually gives you this formula. And one more assumption that is important, you also assume that the number of samples is much larger than the number of parameters, which is fine if you have 2 parameters and 1,000 samples, but in machine learning it's not fine, right? So, but deep learning is high dimensional and over parameterized. So many parameters, large dimension, not so many samples. So even if this formula is true in many cases in physics, in current deep learning this will not be the case. So that's what kind of brought us. Now I explained that even the simple case of just linear regression is not as simple. And so that's what brought us kind of revisiting it. So, and actually trying to understand how the different methods are working. So in this paper, we take a very simple setting. It's a toy model of, there needs to be enough non-triviality for the results to be, interesting, but as simple as possible so that this is true. So we take a case where the inputs are IID Gaussian, so no real images, it's just random noise, the inputs. There is actual random noise, the Xi, and we take these ground truth parameters also at random. So we fix them, but we draw them from some random distribution. And then the labels are created like so, with the sine function here. So there is a really simple, if you want single layer neural network that is actually creating the labels with some ground truth values W star. So that's our assumption now. We will now be working in that kind of, in biology people work on model organisms, so that's our kind of model, right? There are 2 ways to use the word model. One is you simplified everything, and the other one is what is the loss you're actually minimizing. So this is our model. And so then the questions are, more basic question, what is the best achievable error given a limited number of samples? So if you don't have much more samples than the dimension, what can you do? And how do you quantify uncertainty coming from the fact that you have limited number of samples? So under this model, we can actually get a proper answer, and the proper answer comes from the Bayesian inference. So we write the posterior probability distribution, and here we know that our labels were created from a given probability distribution that was just stated on the previous slide, so we use that knowledge, write the likelihood, the prior, the normalization, this gives us the posterior. And then we know it's a few line proof that the optimal predictor, like statistically nothing can beat the predictor that computes averages over this posterior of the sign of your new sample times the vector of parameters over which here we are averaging. And since now I chose it to be a classification problem, just 2 labels, if I have the average, I also have the variance. So the uncertainty here will be just linked to the average here this way. So this is a setting where it's very simple, but we have the proper notion of uncertainty for every typical test sample. Now there is one caveat here. I said that things will be high dimensional. Computing this average in high dimensional setting takes exponential time. So this, this is simple, but I still did something non-trivial. But that we actually know how to deal with. And there is a whole line of work that is kind of closely linked to the field from which I come from, where we have actually exact characterizations of these high dimension limits. And here I just give 2 papers. One is from '89, where kind of this line of work was started in the context of neural networks. And this is one of our group from a few years back, where we kind of rigorously settled down this set of, this theory that it actually works and it's actually correct and rigorous. So in this limit, when we have large dimension and large number of samples, but proportionally so, we know how to say essentially everything about this toy model. And here, that's just kind of schematically said, there is some replica symmetric free energy that in this limit describes both what is statistically the best achievable error and what a given algorithm that we call approximate message passing achieves. And sometimes they are not the same, but there is we also believe they would not be a better algorithm in this case. And this algorithm, when I just kind of show again, in a schematic way, the pseudocode. The nice thing about it that it not only actually gives you the estimator, but it gives you also the variance. So even if it was not a binary classification, but generic regression problem, we actually have in this algorithm both the means and variances, but under the assumptions of this toy model. Okay, so this is not the generic uncertainty quantification method. The way we will be using it, we actually have enough non-triviality in this toy model, and we have now the baseline. This is the uncertainty that we would want, and here it is tractable. We can compute it. We have theory for that, and we will now be comparing the methods that people are using to this to understand how well they are doing. It's kind of our baseline, okay? This is not yet telling us how to do. If none of them works, this absolutely tells us nothing about what to do instead. So that sadly will be the conclusion. But at least we kind of can clearly see that, by a big margin, none of the proposed things actually work. So what we will start with comparing will be this logistics course, right? So I'm back. So now the data come now from the model, and I understand everything about what the uncertainty actually intrinsically is there in that case. But I can still take the data and run logistic regression on it, right? Nothing prevents me from that. And that means just minimizing this loss. And I will be looking at 3 different cases. Even I don't regularize at all. So usually when we train neural networks, we don't add this weight decay, right? That's mostly not there. But it will be interesting to also look at the cases where we regularize. And now, even in this simple setting, we can regularize in 2 quite different ways. Either we choose the regularization parameter that minimizes the test error or maximizes the test accuracy, or we choose it such as it minimizes the test loss. Right? And the loss is this bizarre logistic function, so it's not the same function as the error. So these 2 lambdas actually are not even the same. Okay? So we will look at both of them. So let's start now. Now the way I present the results is in this kind of plots, where on the y-axis here, I am plotting an oracle probability that the new data sample is in class 1. So that's if I actually knew the W star, right? I knew really the ground truth parameters. That's the intrinsic uncertainty that I, by definition, put in the model. So that's the y-axis. And then it depends how well the sample is aligned with the W star. It may be big or small, right? That will depend on the draw of the new sample. And then was on the x-axis here, that's the uncertainty of, that's kind of the baseline uncertainty of the Bayesian estimator that optimally takes into account the fact that here we do not have infinitely many data. We only have 10 times more samples than the dimension. So still quite a bit more, but not infinitely many more. And so we already see, right, that's already not enough to kind of get 0 test error. And we also see that these oracle uncertainties and these base optimal uncertainties, they are, what is this? This is just a histogram, right? So this is a probability distribution. Here it's from a simulation, here is from a theory. And kind of more yellow is that happens more often, and black is that never happens. But we see that it is spread, right? We don't have a line here. If we had a line, it would mean that we are exactly predicting the oracle uncertainty. That's not happening, and it cannot be happening because we only have limited amount of data. But what we see actually, this line here, that's not just a diagonal, that's actually the calibration line. So that's the same line as in this plot of ChatGPT. If it is a straight line going through the diagonal, then it's well calibrated. And if it is not, then it's miscalibrated. So we can prove actually that in this case, indeed, as we would expect, this optimal estimator indeed is well calibrated. So that's kind of just consistent. So far I didn't say anything about the other methods that estimate uncertainty. So that's what I do now, because now what I compare is the oracle probability as before, but now compared not to the base optimal uncertainty, as we can analyze it in the model, but to the logistic score, to this kind of most naive method that you actually output to get the 99% gibbon. And that's the x-axis now, right? And now this is not even so over-parameterized, right? I have 10 times more samples than parameters. So this is still tenfold under-parameterized. And yet, when I compute now the calibration curve, which is just, right, just the average of the y-axis given the x-axis, it actually has this shape that it is above the diagonal when the probability is smaller than half and below the diagonal. So it has this shape of the overconfidence. So this just confirms what I kind of told you. Naturally, we expect that just by optimizing the logistic loss, which has nothing to do with kind of computing the right scores, indeed we get an overconfident scores. And what is then the right-hand side here showing is when we actually compare the base optimal uncertainty to the scores. So now we see that the spread is much smaller. So that's reassuring in the sense that they both are kind of capturing in a similar sense the effect of the fact that the amount of data is limited, but the calibration curve is exactly the same in the two cases. And that again is something that in this case we can show. So we still see that, compared to the perfect way of estimating uncertainty, these scores are overconfident. So that's what we expected. So now let's just look what the regularization does to the thing, right? Because that's kind of the first thing we may want to add and see if it helps. And it helps greatly, actually. If we now just did logistic regression that is optimally regularized, and again, I have these two cases. Either I optimally regularize, either I cross-validated on the error, or I cross-validated on the loss. These are two different things. But in both the cases, this probability distribution is essentially diagonal, or very, very close to diagonal. So in this toy model, proper regularization mitigates the overconfidence greatly. And we don't need to do much more, just regularize well. And here, there's just a plot showing us that regularizing with respect to the loss seems to be a better idea in most cases, but not always. We also have some cases where regularizing with respect to the error may be better. And then, okay, so that was kind of our first exploration. Then we had a bunch of follow-up works where then because I said this is not even yet an over-parameterized case. So then we properly went into an over-parameterized setting that we still can understand in detail and solve, and showed in this paper that, a whole range of Bayesian methods and empirical and many things that people are suggesting in practice for much more complicated models that actually don't work, that they don't compare well to our kind of baseline uncertainty. So that was in this paper. In this paper, we then analyzed the ensembling-based methods such as bootstrap and subsampling and jackknife and all kind of these methods that you may have seen for uncertainty estimation. And again, in this toy, but not so toy because it's high dimensional and the sign, the classification makes it non-trivial. Again, we show that it's not working. The guarantees that we have in the setting where number of samples are large and number of parameters is small all go away. And if I have one more minute, which probably I don't have, I wanted to tell you briefly about the third paper that is about this temperature scaling, which is an interesting thing. So that's the paper that kind of promoted it. And they say temperature scaling submethod is the simplest, fastest, and most straightforward of the methods, and surprisingly is often most effective. Okay, so I'm somebody very suspicious of things. So when I read this, I was like, okay, we will show that this is just wrong and this doesn't work. Because also the idea of it is really, really simple. It's you take the logistic scores and you add a parameter 1 over t there. So, right, if this was some kind of a Boltzmann measure, this would be a temperature. But again, right, I'm not saying this is a Boltzmann measure, but that's kind of the idea. You add there a parameter, and then you choose the value of the parameter so that your validation loss is minimized. And that's the method, that's temperature scaling. Well, we actually found that from all the methods that we tested, this does the magic, at least in our toy model. So that completely, okay, we still don't know why, but we said, okay, if this does the magic, can we do something that to us seems no, why doesn't it go forward? I probably pushed something silly. Okay. Now it goes forward. So what seems important in the temperature scaling is that you tune this parameter to compare something on your validation or test loss. And we said, okay, but why the test loss? That seems a bit arbitrary. But rather, what if we did the following thing? We actually have our uncertainties. And you see, if we had the right measure of uncertainty, we would not need the test set to start with, right? Because if we knew how certain or uncertain we are, then we would just compute it, and we would not need the labels on the test set. So the least we can do is kind of impose this not needing the test set, the condition that if we had a perfect uncertainty measure, we can impose it on we can choose the parameter so that the average uncertainty actually agrees with the average test error, with the test error. And that's a similar idea to the temperature scaling, but it's something that, in physics, we like to call this the Nishimori conditions, coming from some work in physics. And in statistics, this is actually really close to what in statistics people call the conformal prediction. And we found that this works even better than the temperature scaling. So again, it does the magic. It's very simple. You just need to choose one parameter at the end of your training. And these are, some validation on very simple neural networks, but not as toy as the one that we played with. And the numbers here are low is good, so this is without any calibration, so it's not so low. Then temperature scaling improves it, and this expectation consistency improves it even more. So I'm not saying that this is solving the question. It's not solving the question by no means, but at least in our kind of simple exploration, this kind of surprised us that it actually works really well. I will stop here with giving you back the references.
Okay, thank you very much.